All right, everybody, here we are for lesson 3, defining acids and bases. This is going to be a real quick lesson here. So acids and bases have been defined for a long time. One of the definitions that we've used in the past was the Arrhenius definition. So the Arrhenius definition was simply that an acid was defined as any substance that when dissolved in water, so notice that it is water-based, releases hydrogen ions or increases the hydrogen ion concentration. So this is not that far away from what we're going to, the definition we've been using so far. So it's anything that releases hydrogen ions or increases the hydrogen ion concentration. So hydrochloric acid, of course, it is producing hydrogen ions, so it is clearly increasing the amount of hydrogen ions in solution. All right, acetic acid, also same idea. Ooh, I really don't like how they wrote it here. This is not my favorite. You'll almost always find acetic acid written as CH3COOH, like so. This doesn't even, yeah, well, what a weird way of writing it. Okay, I like it written out as choo-choo. Okay, so there the hydrogen comes off of that extra oxygen. We've talked about that in a previous lesson. And then, according to Arrhenius, bases were defined as substances that release hydroxide ions. So Arrhenius was defining these two chemicals by the two different products that they produced. This is the trick of it, is that the next definition is going to narrow this down to be just about one part of the reaction. So here we have some sodium and some hydroxide. So this is our sodium hydroxide up here. And once it's in solution, it dissolves and it separates, and we end up with little hydroxides floating around in addition to the waters, and that is making it basic. Now, ammonium is something that we've already worked with. Does not really produce hydroxide in such a straight manner. Ammonium here absorbs a hydrogen off of the water and forms ammonium hydroxide. Ammonium hydroxide. And then those hydroxides are then the byproduct. But in reality, there's no real stopover at the ammonium hydroxide position. It really just jumps straight over to this. The ammonium just simply removes a hydrogen off of, so we can kind of think about ammonium is like this. Now I'm going to go full bore. Ammonium actually has a pair of extra electrons. Remember that nitrogen has 5 valence electrons. So these 5 valence electrons are around ammonium, and then there's a hydrogen over here, and essentially the hydrogen is going to leave the water to join up with that lone pair, that pair of electrons on ammonium. So you end up with an ammonium that has 4 hydrogens on it, and a hydroxide of a water with 3 full pairs of electrons. And that's where this negative charge, this positive charge comes from. Anyways, so it's a direct reaction. These two bodies will not stay together. They'll be separated after the reaction is complete. So Arrhenius definition doesn't really describe this properly, right? There's no release of hydroxide. So they thought, okay, well, there's got to be some other way this happens. And there's even some other examples like baking soda, which is sodium bicarbonate. It also is apparently basic, but the hydrogen ion is not released. What's going on there? Metal ions like iron 3 and aluminum, they tend to turn litmus paper red, so suggesting that there are acids, but there's no hydrogen ions in an iron. This is just an iron ion floating around. This is just an aluminum ion floating around. So what's going on? So Bronston's Lowry definition was a little more useful. He says that acids are anything that donates a proton and bases are anything that accepts protons. This is a much more useful definition because it applies to essentially every situation that we can think of. So here we can see, here's the little diagram I drew earlier of the ammonium absorbing the hydrogen to become ammonium hydroxide. And that is an accepting of hydrogen. So bases have a strong desire for protons. We can extend this definition a little bit because now we can also apply this definition to anything that has a hydroxide as well, right? Because essentially now we can think about KOH. KOH becomes K plus OH minus, and then if you mix that with water, the OH here and the water, they will react, and this OH will absorb a hydrogen. So essentially there's less hydrogens floating around. This doesn't actually go anywhere. This just becomes another water and an OH, but that will continue forever. And so effectively there's one less hydrogen out there in the water when you mix in KOH. So the Bronston-Lowry definition still applies to something that is technically an Arrhenius base. Bases have a strong desire for protons, so much so that if they are strong enough, they will steal protons from the acid and combine it with itself. This is essentially a measure of bond strength. So this desire of protons, this is a measure of that hydrogen molecule bond strength. In a strong acid, the bond strength between a hydrogen and oxygen is weak in the molecules, so that bond breaks. In a weak acid, the bond will be weaker. And we should actually say that a base here, let's actually add one more line here that says that a strong base on the by the same hand, strong base is something that makes very strong bonds, makes strong H molecule bonds. And a weak base makes weak bonds. And that, of course, follows with our idea that the opposite of that once an acid has lost its hydrogen, it becomes a base with the opposite strength. So a strong acid that loses a hydrogen becomes a weak base. A weak acid that loses a hydrogen becomes a strong base. So this now adds up to why hydrochloric acid is so dangerous. It's a strong acid because the ionic bond between the hydrogen and chlorine, we can even go back to Unit 1, we can calculate that using electronegativity differences, seeing how it's much weaker than the hydrogen fluoride bond, which is practically a covalent bond. It's in the covalent bond strength range. And so hydrofluoric acid becomes a weak acid, and hydrochloric acid becomes a strong acid. We're really talking about what is essentially bond formation. Bases absorbing hydrogens is a bond forming, and bond breaking with the hydrogen being donated by the acid. So in some compounds, this bond energy that's being lost or gained is pretty much the same. This is what we call an amphoteric substance. So here we have something like bicarbonate. Bicarbonate can gain a hydrogen almost just as easily as it can lose a hydrogen. It could also could steal a hydrogen from. So here we have it stealing a hydrogen from water to form hydroxide. So here it is giving its hydrogen over, acting as an acid, so that hydrogen is really not particularly strongly held, so it can be released to water, but it also has this negative charge which allows it to steal a hydrogen from the water. And so that's called an amphoteric substance. There's quite a few of them, but this is one of the examples. All right. So this is going to be where we start talking about the conjugate base pairs. I've already hinted at this, but this is what's happening. If you have a base and that base absorbs a hydrogen, it now has an extra hydrogen, and it has become a conjugate acid. An acid that loses its hydrogen will now have a spot where a hydrogen used to be, so that makes it a base. So we can reverse this process. We can look at this ammonium ion here as being an acid donating to the hydroxide, and in the case that it's donating to the hydroxide, the ammonium is the acid and the base is the hydroxide, and that makes this the conjugate base and this the conjugate acid. And of course this makes sense because that's the titles we gave it earlier. Okay, so for any reversible acid there is going to be, or for any acid, we can treat the produced products, particularly the produced salt, as going to be the opposite designation. Here we have the general form. If we are using a general form, here is an HA, so something that has a hydrogen to donate. Here's a B, something that can absorb a hydrogen, or accept a hydrogen should be the word. And we can see that the acid is going to have a conjugate base. This A minus can very easily take on a proton, and also this water that's acting as a base here can just as easily lose this proton once it becomes hydronium. Same thing with the base. So here we go. We can see that I've labeled these out, defining the acids and bases. What's probably the most interesting part is something I had suggested earlier, that if you have the case of something strong, like let's look at this acid here. So this is a strong acid. So this is a strong acid. And what you'll actually find is a strong acid produces a weak base. And this makes sense because the bond in the strong acid is strong, or a strong acid has a weak bond between the hydrogen and the molecule. So then that means that the bond that can form from the conjugate base is weak. Similarly, this water, which is in this case is a weak acid, or a weak base, you also end up producing, I believe in this case, this will also be weak, or strong, I guess. It has to be strong, otherwise I'd be going back against my word. Sorry. It's strong. Unless it's amphoteric. Oh, water's amphoteric, that's why. So water's special. Let's not look at that one. Don't worry about water. Water's amphoteric, so it's weak in both cases. All right. Here we can see we've got some Arrhenius. I've defined these. I looked at this and I thought, a little strange to break the definition of Arrhenius and Bronsted-Lowry. You'll find that almost everything counts as Arrhenius and Bronsted-Lowry in the acid side, because acids in general are, because both definitions define acid the same way, proton donors. So all of these are Arrhenius acids. They all are donating protons. And then this base down here, though, is a proton acceptor. So this is the only base that follows the Bronsted-Lowry, but not the Arrhenius definition. I think we need one more example here. So this is my favorite example, which is boric acid. So boric acid is BOH3. And you'd look at that and you'd say, well, that certainly looks like a base to me. How come it's called boric acid? Boric acid. And so boric acid, when reacted with water, does not release any of those hydroxide. Boron is a very small molecule. It only has 3 electrons. It doesn't want to lose any of those electrons if it can help it. In fact, because it only has those 3 valence electrons, it actually has a lot of space around it for more electrons. And so boric acid will actually become a borotetrahydroxide ion. So here we can see that it's accepted an entire hydroxide onto it. Well, what's the byproduct of that? The byproduct is an extra H plus in solution. And so there is your example of a Bronsted-Lowry acid. It's an acid that produces protons in solution, but not by donating them. So there you go. That's a little bonus for you. I'm going to try to add that to the next version of this, I think. That's it for this this lesson. It looks like I've done all the homework too. So just try to get used to those definitions.